This podcast is about bond and molecular polarity. So we're going to look at polar and nonpolar bonds and polar and nonpolar molecules. So electronegativity, which we saw in the periodic table unit, is a measure of how much a bonded atom pulls on electrons that are shared. So we only look at bonds when we talk about electronegativity. We use the Pauling electronegativity scale, which typically ranges from 0 to 4, depending on which one you look at. I like this one because it sort of gives you a picture representation. The higher the block, the higher the electronegativity. Fluorine is the highest, and then the metals over here in this corner are the lowest. Notice it doesn't have the noble gases because we don't normally talk about how they bond. So bond polarity, if you have atoms of unequal electronegativity, they can make a covalent bond, but it's not going to be shared equally. So there's a couple different ways to draw this. You can label we call it a polar bond because it's uneven, and you can label it with these little Greek symbols. Delta plus means partially positive. And in this case, hydrogen is lower electronegativity, so it gets the partial positive. And then the partial negative means the delta minus is partially negative. And in this case, the fluorine gets that one because it holds more of the electrons because it's more electronegative. So think of it as a tug of war where fluorine pulls more than hydrogen does. Another way you can label the bond is this polarity arrow, which puts the arrow end towards the negative side, and then the positive end gets a little plus. So in this case, fluorine is more electronegative, so it gets the arrow end. And you can determine the type of bond by calculating the difference in electronegativity, and that's the absolute value of the difference, delta En, and that's the change delta, capital D, change in electronegativity. So we are going to use this table, this Pauling electronegativity values table, because it has 2 decimal places, so we get a little bit more sig figs. And the way we're going to look at it is if it's a polar covalent bond, and remember that polar means uneven, it means that the difference is higher. And in this case, most books define a polar bond where the difference is 0.4 or greater. The difference in electronegativity. So an example of that would be an HCl bond, and hydrogen is 2.20, chlorine is 3.16. The difference is 0.96, so it's definitely greater than 0.4, so this would definitely be a polar bond. And because chlorine has a higher electronegativity, it would get the arrow end of our polarity arrow here. If it's a nonpolar bond, the difference is going to be lower than 0.4, and there are not very many examples of this, and one of them is pH, and those have 2.19, 2.20, very, very similar electronegativities, so it's 0.01. Most common, the most common type of nonpolar covalent bond is when the 2 atoms are exactly the same, so the delta would be 0, and it doesn't matter what the atoms are. If it's an ionic bond, one of the definitions of an ionic bond is a difference of greater than 2. But we are also going to consider it an ionic bond if one of the atoms is a metal, and it doesn't really matter what the difference is. So if you've got a metal, don't even calculate it, just call it ionic. And one example would be NaCl, which is definitely greater than 2. So to practice, using the Pauling electronegativity values, go through each bond and calculate the delta, calculate the difference, and in each pair figure out which one has the most polar bond. Because that's usually what we're doing. It's not really about the numbers, but it's about which one is a greater polarity or higher difference. So CCl has a difference of 0.61, which is polar. Si is 0.08, which is very tiny, and so the more polar bond would be CCl. In this case, Ni is almost polar, it's 0.38, and F is definitely higher, 0.94. And in this case, SH is 0.38, which is not a very polar bond. However, two F's together has a difference of 0, so it's the lower, so this is the more polar bond. And again, both these bonds are polar, but OH is more polar with 1.24. So a molecule is polar if it is unsymmetrical, and it's more polar if it has really polar bonds. So a polar molecule has what we call a dipole, which means that that it is uneven. So here's an example of a polar molecule. It has a lone pair on top, which is not shown, but that makes the shape trigonal pyramidal, which means it is unsymmetrical, and because it has polar bonds, the dipole points towards the green guys, which means for NF3 that the dipole goes in this direction, that the green fluorines are more polar than the positive nitrogen side of the molecule. So we say that it has a net dipole, or it has a dipole, or it is polar. All those things mean exactly the same thing. So what you want to do here is draw out each example, use the shape, figure out what the shape is, draw the molecule, figure out if the bonds are polar, and then look at the overall shape and figure out if the molecule is polar. Stop here and work on it, and then turn the tape back on and check and see how you did. Okay, so what you want to do here is look at the bonds, but more than that, look at the shape of the molecule. So CO has polar bonds, therefore they get the arrow, but because CO2 is linear, it is symmetrical, and these two arrows are going to cancel each other out because of symmetry, and it is a non-polar molecule that does have polar bonds. Water, on the other hand, has polar bonds, OH, but because it has the lone pairs on oxygen, it is unsymmetrical, and it is a polar molecule, and water actually is very polar. CHCl3 is tetrahedral, which is a symmetrical shape, but in this case it has 3 chlorines and 1 hydrogen, so it is unsymmetrical, and it is polar. If all of the atoms on the carbon are chlorine, we've got 4 chlorines. It is symmetrical because all the angles are equal. Symmetrical means it's nonpolar.